Good afternoon, dear students and my colleagues. Today I read a lecture. My name is Номоев. The name of my lecture is Synthesis and Properties of Composite Nanoparticles, Core Shell, Hollow Silica, Janus-like nanoparticles. This lecture is based on two articles published in the scientific journal Technical Physics Letters. The first article is Synthesis and Properties of Hollow Silica Nanoparticles, published in Pledis Publishing. And second articles with Sueza, Sergei Prokofьевич Prodakhanov, synthesis and structure of silver silicon nanoparticles obtained by the electron beam evaporation condensation method. This article published in Technical Physics Letter, in journal Technical Physics Letter. Following slide. Experimental set for obtaining nanopowders consists of the following part: electron accelerator, the sample, evaporation chamber, coagulation cooler, and volume for nanopowder. This place. Now I will tell the basic principle of experimental set for obtaining nanopowders. Electron beam from electron accelerator irradiates sample, vapor from sample, moving to coagulator cooler, and collect in this volume. Vapors of the sample moving in the long tube. Name of this long tube coagulator cooler. The vapor are coagulated in this tube and transformed into nanopowder. Nanopowders are collected in the cylinder. This volume is named cylinder. Do you understand?
Yes.
Electron beam from electron accelerator follows to sample. Sample is evaporated. Vapor from this sample moving to the tube, long tube. In this tube, vapor is coagulated, and then forming nanoparticles put on this silo, and in this place we can see nanopowder. Do you understand? Following slide. In this slide we see experimental set photo. The sample is placed in the sample. The sample is placed in the evaporation chamber. Electron beam irradiates the sample. Vapor from this sample moving in the direction to cylinder. In this direction to silo. To silo. To the silo. The interaction of relativistic electrons with matter consists of two types: the ionization and radiation loss of energy, and given by the formula Bethe-Bloch, and are given by Bethe-Bloch formulas. This is ionization loss, this is radiation loss. The ratio of radiation losses and ionization losses is very small for cuprite. This ratio is equal about 10, is very, K is equal about 10 in power minus 2. So main part of electron energy is converted in ionization losses. The electron pass in cuprum sample is about 2 millimeters. The way of electron in cuprite is about 2 millimeters. The electron energy was 1.4 mega electron volt. The beam current was varied from 3 to 10 milliampere, and the maximum power density was 10 watt per centimeter square. Following slide. In this slide, we see real image of experiment. On the top left, we see sample after electron irradiation. At the bottom, we see image-less heated sample. The following slide. Obtaining commercial silicon dioxide nanopowders. They are obtained by evaporation initial solids with an accelerator of electrons with the usage of highly pure quartzites from Cheremshanskaya deposit in Republic of Buryatia. The production uses evaporation of the initial solids under the influence of a powerful relativist concentrated electron beam in the conditions of atmospheric pressure. Further, higher temperature steam is rapidly cooled by carrying gas. Then the substances condenses and hardens. As a result, nanoparticles appear and get located, finally making up a powder-like product. By this industrial commercial method, we can produce 15 per hour. At the bottom, on the right and on the left, we see silica nanopowder in cask. In Russian, bochka. Following set. Synthesis and properties of composite nanoparticles. Argentum silicon. Alloys of silver silicon model eutectic system are of interest both for basic science and technology applications. A higher photosensitivity of silver and the presence of giant plasmon resonance in the visible spectral range account for the increasing use of silver in optoelectronics. The intensity of fluorescence from praseodymium 3+, lanthanum 3+, and other emission centers increases on the surface of silver silicon nanoparticles. This enhancement is due to the appearance of surface plasma resonance of silver silicon composite nanostructures. The use of pure silver nanoparticles as biosensors encounters one very serious problem. Nanoparticles liberate silver ions which are toxic for the living cells. However, the thin continuous silica shell minimizes the release of toxic ions while retaining the optical properties of silver-based biosensors, and in addition decreases the size and reduces the agglomeration of nanoparticles. For this reason, in recent years, the synthesis and characterization of silver silicon composite nanostructure, including core shell nanoparticles, have received much attention from researchers. Following slide, please. In this slide, we see a scheme of obtaining of silver silicon in graphite crushable. One. This electron beam irradiates two substances, silicon and argentum. One is graphite crusher. Electron beam falls to this two substances, silicon and silver, argentum. Do you understand? In order to silicon contact it with silver silicon sample is put on silver substances. B. Plot of the temporal variation of electron beam current for the evaporation condensation of silver silicon core shell nanoparticles. In this direction, we see current milliampere. In this direction, x axis time minutes. At the first time interval, 0.7 minute, silver and silicon are melted together. And the second time interval, current is increased. In this time interval, two substances, silicon and silver, evaporated, and then coagulated and formed nano powder. Do you understand? At the first time interval, 0.7 minutes, silver and silicon are melted together. Liquid formed liquid state. At the second time interval, current is increased. Composite vapor from these substances, argentum and silicon, are produced in second time interval. In the present work, third generation nanoparticles, core shell, Janus-like, hollow silica, was characterized by a combination of methods, including transmission electron microscopy, TEM, high resolution transmission electron microscopy, selected area electron diffraction, and energy dispersive X-ray fluorescent analysis. These methods we used in order to characterize nanopowders. At the bottom of this slide, we can see the electron microscopy. Following slide. Then image showing silver silicon core shell nanoparticles. Then image showing core shell nanoparticles and silver nanoparticles only. Squares 1, 2, 3. Squares 1, 2, 3 indicate areas used for SAED measurements. On the left of this slide, we can see black core of argentum and thin shell, and silicon thin shell. Do you understand?
Yes.
Following. Then image core shell, cuprum, silicon dioxide. We can see core, cuprum, and shell, silicon dioxide. The diameter of core shell nanoparticle, this core shell nanoparticle, is about 100 nanometer. This distance, 200 nanometer. This particle, the distance between this line, 100 nanometers. Do you understand? In this experimental set, we produced the same core shell nanoparticles, cuprum, silicon dioxide, and silver, silicon. Following slide. The temperature dependencies of the surface tension of cuprum, argentum, and silicon. In this slide we can see when temperature is increased, surface tension is decreased. Do you understand? But ratio between surface tension cupride, argentum, silicon is constant. Distance between cuprum, surface tension, cuprum, silicon, and silver, when we rise temperature, is constant. Do you understand? Formation mechanism core shell nanoparticles. Shell is formed from a material with a lower value of surface tension. Low value of surface tension. Ratio between surface tension, cuprum, argentum, and silicon remains constant at all temperature. Follow slide. Core shell nanoparticle. core shell nanoparticle. Shell is formed from a material. Shell is formed from a material with a low value of surface tension in accordance with the first principle of thermodynamics. Silicon surface tension is lower than cuprite. So cuprite is core and silicon is shell. Surface tension of silicon is lower than surface tension of cuprite. You understand? And so silicon is shell. Because in accordance to first principle of thermodynamics, this system have low energy. Do you understand? There's low energy. Following step. The histogram of particle size distribution. In this slide, we can see dependence from this size nanoparticles, and this line is counts of nanoparticles. Nanoparticles, cuprite, core cuprite, silicon dioxide is shell. Do you understand? Following slide. The function of particle size distribution. The function of particle size distribution corresponds to log normal distribution, to log normal law. The function of particle size. Back. This is log normal. This is log normal function. Do you understand? Following step. Formulas of log normal distribution. This formulas. Do you understand? This is Gauss formula. Following step. Janus-like nanoparticles. Tantalum silicide, silicon. Same image. This image made from electron microscopy. Do you understand? Janus-like nanoparticle consists of two parts. The first part is silicon. The second part, black part, is tantalum silicide. Silicon is dielectric metal. Tantalum silicide is metal. Then silicon haven't free electrons. Tantalum silicide haven't free electrons. So this nanoparticles is named Janus-like nanoparticles. Janus-like nanoparticle because this particle have two phase. One phase and two phase. One phase is dielectric, two phase is metal. So this Janus-like nanoparticle have unique properties. They nanoparticles have very big dipole moment, electrical dipole moment, and application of this nanoparticle is very is very big. It's very big in optoelectronic and liquid crystal. Janus, like nanoparticles, have big applications. Compound tantalum silicide silicon 40 after evaporation condensation experiment. After irradiation sample, tantal and silicon, after evaporation condensation, we can see this compound, two substances in graphite crushable. Do you understand? Graphite crushable. Follows it? Size distribution, tantalum silicide, Janus like silicon, Janus like nanoparticle, tantalum silicide, silicon. In this, on the left slide, on the left part of slide, we can see log normal distribution, log normal distribution. And on the right part of this slide, we can see Gauss plot. The function of particle size distribution is corresponded as well to a log normal law as a Gauss. Do you understand? Following set. Scheme of formation core shell nanoparticles and Janus-like nanoparticles. Beam of electron, graphite crushable, two substances, maybe cuprite, silicon, maybe silver silicon, maybe tantalum silicon. Do you understand? When electron beam irradiates two substances, we can see formation vapor from these substances. Vapor. Nanoparticles, particles of this vapor coagulate each other and form nanoparticles. The nanoparticles form core shell structure. Two ways formation of core shell structure. Cuprite silicon dioxide and argentum silicon. And third way, we can see from formation Janus-like nanoparticle. Do you understand? These articles are also capable to reducing of dangerous substances. Vapor from substances are condensated. Further particles coagulate with each other and form nanoparticle which have core shell or Janus-like particle structure. If substances chemically active, we can see formation Janus-like particles. In other case, core shell structure. If tantal form chemical compound with silicon, we can see Janus-like nanoparticle. In this way and second way, cuprum and silicon dioxide is not form chemical composition, and we can see core shell structure. Do you understand? Following slide. Synthesis and properties of hollow silicon nanoparticles. In this slide on the left, we see transmission electron microscopy image hollow silica nanoparticles and core shell particles, core shell nanoparticles. In this slide, we see shell, silicon shell. The diameter of this shell nanoparticle is about 200 nanometers. Do you understand? But in this image, we can see core shell nanoparticles. In this cuprite and in this silicon shell. Do you understand? Following slide. Hollow nanoparticles are promising means of delivery of active substances to a target organ for treating disorders, forming images and placing markers. These articles are also capable of reducing of inflammability of dangerous substances. Well-known hollow silica nanoparticles of the Silinax type are characterized by a record high specific surface at 500 square meter per gram, low density 70 gram per liter, higher porosity, large specific volume of pores, 9-13 millimeter cube per gram, and ability of absorbing liquids, 360-400 milliliter water per 100 gram nanopowder. Using these hollow nanoparticles as structural elements, it is possible to create promising devices for various applications. Do you understand? No? Little.
Yes.
This is example of application of hollow nanoparticles. Application of hollow nanoparticles in optoelectronics, in medicine, in catalysis, and other industrial spheres. Do you understand? Following. The core material, core material then escaped from the shells was removed from the powder via the following nanochemical reactions. Concentrated this liquid, and then we obtain these substances. Following slide. In this slide we can see hollow nanoparticles transmission electron microscopy image. On the left in this slide we can see a big number of hollow nanoparticles. These particles have different size, from 1 nanometers to 300 nanometers. Do you understand? The following slide. Thank you for attention.